So that was an introduction. It's fairly high level. I've tried to kind of keep it, not getting into too many specifics, but give you a flavor for the sorts of things that you're thinking about. We're going to revisit a lot of this in what's coming. But you do need to be conscious of the hardware. A GPU is a different hardware to a CPU. You need to be conscious of those differences. Things will run if you're not conscious of those differences, but in order to get, but the performance will be absolutely rock bottom. To get good performance, you need to be conscious of these things and think about it with your application. But that's true whatever programming model you use. So was that the right level? Too detailed, not detailed enough? I mean, at the back, you've never used GPUs. Was that helpful or put you on the spot here? Please ask questions as we go along. Yes? Yes? That would be a matter for NVIDIA to answer. This is a slide from theirs. I didn't actually count them. Yes, there are 15 there.
Yeah.
Right. I got the number wrong, sorry. Sorry?
Should be.
Yes.
But that's not one of the, you will run in one of your examples, right?
Yes. There are tools you can use to find out exactly what the architecture looks like. I mean, you don't need to know that number particularly. I mean, it has some bearing, but you don't need to know it in order to run your code. But it's true. I mean, that's an inconsistency of what I said. Yes, there were 15 there. So part of today is to do some actual exercises and actually get you to try some stuff. But if you're going to try some stuff, before you do that, you actually need to know a little bit about how to use a Cray XK7. So this lecture is not really OpenACC, it's not really hardware, it's, it's kind of just getting you up to speed in order to do the exercises. But also, if you're going to do future work using a Cray XK7 like Turdy or other machines, then it's useful just to know how you do the compilation, what the right command is. The practical exercise, I mean, we don't have much time today, and my view is that you've come here to learn OpenACC, you haven't come here to learn how to use the Slurm workload management system to queue your jobs, or you haven't come here to learn exactly what the compiler flag is for this or that. So the exercises that I've done have automated a lot of that process. It's not hidden, it's there. You can do it yourself if you want. But to kind of make the most use of the time we have, there are makefiles and job scripts that do some of this for you, and you can use them as templates. If you really want to type the commands yourself because you feel happier doing that, you can do that. They're there as a tool, they're not essential. But it's probably important, when you go away to do your own project or to do your own code, that you know how these things are done. You can either use what I've got as templates or some of the information here. So this Cray system you're using, I say it's a small Cray system. Actually, again, that should have come out. Normally, these exercises are done on a small system called Raven that we use. That's a Cray system that's only got 8 nodes. Here, we've got a system with 3 cabinets. So that, what I say small there, is in fact a mistake that's left over when I converted the slides. You log in and you compile. You don't compile on a node with a GPU. You compile on a CPU, a front-end node. So you don't run jobs there. The jobs run on the so-called compute nodes. These are the nodes that actually have the GPUs. You don't talk to them directly. You submit jobs to them, and the jobs run there. So each one of those nodes has 1 CPU and 1 GPU. You run the jobs through, well, there's 2 ways to run it. You have to use the Slurm batch system. You can either do it by writing a script that submits the job into the queue, the job runs, the result comes back for you. You can use them interactively. I wasn't sure if this would be available, so I didn't use this for the exercises, but the instructions that you've got explain how to do things interactively, where you actually move on to the compute node to work directly. But you don't run your compute jobs just from the command line. They won't work. There are two file systems. There's the home directories, as you'd have as usual. There's also another parallel file system, the Lustre file system, and that's where, in general, you should submit your jobs from. That's where jobs should run. And that's /scratch/turdy/ the username. So you can use $user if you wish. It'll be course 1, course 2, whatever. Your home directories for the course are backed up. The Lustre file system is not. Files are periodically purged. Again, this isn't so important here, but if you're using the Raven system, I always have to say this. Lustre is volatile. Don't leave important stuff there. Keep it on the home directories. I imagine the course directories you're using will be deleted soon after the course ends. So anything that you want to keep, you should copy away to your laptop or a USB stick or a different system that you use, or if you're on Turdy but you have your own account there, copy it into that. But don't assume that it will be there, tomorrow, next week, because these things may disappear. Cray uses a Linux-based environment on the login nodes. You have a bash shell by default. All the usual Linux commands work. The Linux that you're using is basically a SUSE derivative. Software versions are controlled using the GNU module command, so which you can find in a lot of systems. Cray uses it, but it's not Cray specific. If you want to learn more about that, then you can look at the man page. So when you want to choose a particular compiler or a particular compiler version or whatever, you do this by using the module command to swap things in and out. And that changes all of the path variable and everything appropriately. To see what you've currently got, you type module list. If you want to see what's available, you can use the module avail command. And if you want a new module, you either load it up, or if you've already got a version that's going to conflict, like you can't have two versions of the compiler loaded, then you have to do a module unload or a module swap. You can module unload the old one, or you can do a module swap to get to the new one. In order to choose your compiler, the way that's done on the Cray systems is you have a programming environment module, and you load one of these three to decide which compiler suite you're going to have access to. So for these exercises, we're going to use the Cray programming environment. PGI also support OpenACC, but I haven't tested the exercises with the PGI compiler, and so I really would prefer if people used the Cray one for now. I mean, if there are problems with PGI, I'm happy to try and work out what they are and try and solve them, but I think the best use of your time is not to try going into any portability issues today. There's also GCC and other ones. Once you've got the programming environment, the actual compiler is another module within that that's loaded automatically, and for the Cray compiler, it's called CCE. You need to swap to the most up-to-date version of the compiler. So if you want to do things by hand, the most up-to-date version that's on there at the moment is CCE 8.2.0.141. That's not the default one that you get when you log in, so you'd need to swap to that. This is a pre-release compiler. Cray's put this on the system specially for this course. It's what we're using in-house for the most up-to-date stuff. So you're kind of getting privileged access to it for this course. But why not? You should have the best OpenACC compiler to do the course, so that's what we've got for you. What this does mean is that this is a pre-release compiler, so there are no guarantees of this or that or the other. I've tested the exercises, they do all work. But also, any performance figures that you get, I'm afraid you can't go to a conference and present them with that compiler because it's pre-release. So if you really need to do that and you really want to present something, you need to talk to Cray, talk to me, and we can sort out whether you can do that or not. If you're going to do any GPU programming, you need to also make sure that there's a special module called with the unforgettable name of Cray PE Accel NVIDIA 35. If that module is not loaded and you do OpenACC, it all compiles beautifully, it all runs beautifully, but not very quickly, because it's only working on the CPU, because your OpenACC will not be recognized. You always must load this if you're doing GPU work. And it's not, I'm not sure whether it's loaded by default, so you should always check that. When you actually use the compiler, the command that you use, there's some wrapper functions that you use. ftn for Fortran, cc for C, capital CC for C++. You use the same wrapper name, whatever compiler you're using. Doesn't mean all the compiler flags are the same, but you use the same wrapper name. Why should you use this wrapper? Because it takes care of a lot of the linking paths and special architecture flags and things that you need in order to run on this system. If you try and do things and you try and use the underlying compiler, it won't work because you won't have set up the paths correctly. You should also make sure that this module is loaded. That's make sure that you're using the CPU correctly, the right flags are being used. In most cases, you probably don't need any other compiler flags. The default is optimized code with the Cray compiler, the Cray programming environment. If you really want unoptimized code, you should say -00. By default, you're getting -02 with the Cray compiler. OpenMP is recognized by default. If you don't want OpenMP, you have to switch it off. That's another kind of gotcha. The actual compilers, well, these are the names of the actual compilers, and if you want to learn more about particular compiler flags, you can look at the man pages for those commands. I've said about optimization. When you compile with the Cray compiler, you don't get a vast amount of information scrolling up the screen. If you really want to see what the compiler is doing in terms of how it's compiling your code, you need to ask for a compiler listing file, a so-called loopmark file. You add a flag to your compilation, and this will write a new file. Instead of it being test.cc or test.c, it'll be test.lst. And this is a text file. It gives you a source listing that's annotated and lots of explanatory messages. It's a very good idea to look at this. It doesn't affect performance of your compilation, so it costs nothing. I would always generate this. It's really useful, especially for OpenACC. All of the messages that you do get some messages scrolling up the screen. You get a lot more messages in this listing file. They all have a little tag. If you go back to the command line and you type explain, you can get more information about what that error message means. If you want to get the full compiler manuals, you can get them off the web. As I said, you should submit jobs from the Lustre file system. You submit them using, for these exercises, a Slurm job script. So you would do sbatch and then a file, which is the job script. Lots of options to do with that can go into the header. And it'll give you a job number. You can see what's running by the sq command to see if it's finished. And then if you decide you don't want to do it anymore, you can use the scancel command to kill that job. Within the job, the way that you actually run the program, there's a command called apprun that's used. You won't have to do anything with apprun today, necessarily. But if you look inside that, whereas with a cluster, you might use MPI run, AP run is the Cray equivalent of that actually gets the code to run on these nodes. This is more for information. I'm not going to go into this today. If you want to write a Slurm script, this is a bit of explanation about what's going on and how you would do it. And this is a quick example. So in this quick example, stuff up here that says how many nodes do you want? How do you want to use them? And then you could, for instance, run a PGI command called pgaccel-info, and that would tell you something about the GPU. And so apprun, this command at the bottom, is what's actually running your code inside this script. This option here is saying, I don't want to worry about the options for apprun. Just use all of this information up here. So that's very convenient. You don't have to separately specify numbers of nodes and things down here. There's two slides here for compiling CUDA and compiling OpenCL. We're not doing any OpenCL. CUDA tomorrow, maybe, but I put those there for information. People often say, oh, how do I compile OpenCL? what compiler should I use and so on. Since you have the PDFs, I'm not going to talk about that. Here, it's put in really for your information if you use OpenCL or if you use CUDA. So if we go back to the timetable here.
Just one small correction. There's 14 on the XK, on the K20X.
Oh.
We haven't, not 50. I'll come back to that tomorrow.
Okay.
The diagram shows 50.
Right. Well, I stole the diagram from NVIDIA, so I thereby put blame upon you.
So you were correct. There is 50 boxes in there, and but when you run NVIDIA SMI or EGX, you get the 40.
So already we're going a little bit slower than I anticipated. Basically, what we have now is the first practical. I'm not really a C programmer, but I call it Practical 0 and start at 0 because it's not really OpenACC, it's the very basics. The idea of this first practical is basically just to check your account works. So if you don't want to do it, that's fine. But this practical is going to run a script which is going to do two things. It's going to learn about what the GPU looks like by running two utilities. One is from NVIDIA, it's called the NVIDIA SMI, and the other is the PG-Accel info script, which comes with the PGI programming environment. Both of these are very useful if you just want to get some quick numbers about the GPU. So the first practical is simply running a prepared script to give you that information. So you can then look at that information. You can see how many SMXs there are. You can see what the bandwidth is across the PCI Express bus. It does these measurements and summarizes it for you. So in this directory, ~a Hart, Cray _ OpenACC _ slides, as well as a bunch of PDFs. Oh, they've been moved. Sorry, right. In this directory, /project /CS staff /courses, you will find, as well as the PDFs, a tar file. That tar file contains all of the exercises. So when you unpack that, you should get a directory that's called Cray OpenACC training, I think. You go into that, and you'll see there's a license file. Yes. If you break anything, it's not our fault. Cray, I mean. That's the license. All of these codes are taken from, sort of public domain type places. There's nothing particularly proprietary about them. I mean, we've done some work on them, but then you'll see directories. There's a tools directory that contains some generic stuff that is used by the other practicals. And then you've got Practical 0, Practical 1, Practical 2, and Practical 3, and parallel code, which is something for tomorrow. Practical 0, if you go into that, as well as a little README file, there's a submit script. What that submit script will do is make a directory on the Lustre file system for you and tell you what it's called. It will create in that directory a Slurm script, and it will then submit it, and it will run. And when it runs, if you cd into that directory, you should find a .log file, which contains the output from it running. And if you look in that file, you should see a bunch of information about the GPU that's appeared. So if you try that, if it doesn't work, then there's obviously something gone wrong. And if it does work, then you can have a quick look at that information. The first block of information is the NVIDIA SMI. That's some of it's very low-level information about GPU driver numbers and so on. But it also tells you about clock speeds and this sort of thing. After that, you get the PGI information. That doesn't contain so much low-level information. It's a much shorter summary of what's going on. But I've put both in there because it's a useful script to have when something isn't working and you can't work out what's wrong. You can run this and just see whether there really was a GPU attached or if the GPU wasn't working on that node or something like that. So it's a good diagnostic script to have in your back pocket. So that's the reason that that's there. We also have a break until 11:30. It shouldn't take you very long at all to run that script. So mostly I've scheduled practicals before breaks to give us some flexibility. We're already going too slowly. But please, are there any more questions at this stage? Has anybody tried it and it worked? Good. Has anybody tried it and it didn't work? That should be in the Slurm header file. Because I've given this... This isn't OpenACC, this isn't CUDA, this is